Hi, I'm Antonio Sala, and in this video we are going to continue with the case study on controlled and manipulated variable selection in a process subject to disturbances. In previous videos, we discussed sizing for setpoint tracking and for total disturbance rejection, and in here we'll discuss partial disturbance rejection in steady state using polyhedron geometry. This is our model, and these are the transfer function matrices G and H in the above model. We'll only consider the DC gain in here because we are in a steady state analysis. These are the maximum input increments that are allowed from our operating point. This is the DC gain of G, the transfer function matrix from manipulated U to controlled variables Y. And in prior videos we did some input and output scaling. Input scaling will still be of some use in here, and the input scaling matrix is built with the minimum increments to saturation, but output scaling will not be used because we'll neglect such scalings in the polyhedron approach. In a previous video, we discussed total disturbance rejection with some quadratic programming feasibility stuff, similar to the one we are going to do here, and the graphical interpretation of those computations were that the increments of output reachable with vertex disturbances were the cyan polygon in here, changed sign, and the feasible reachable output values with vertex manipulated variable increments were the green polygon. So as the green polygon is much larger than the cyan one, we have a lot of room to indeed cancel the effect of the disturbance, so total disturbance rejection was feasible. So what are we going to do now? In partial disturbance rejection, we are going to state the problem in a different way. For instance, we wish to be able to bring back to the operating point the first variable, if not to 0, to something in this interval from minus 0.1 to plus 0.2. And regarding the second variable, if we cannot achieve 0 error when subject to maximum disturbances, we at least wish to bring the residual error inside the interval from minus 0.15 to plus 0.25. So we'll sum up those wishes as saying that the output, which ideally should be 0, well, we will be happy if that output is in between some minus epsilon low, a 2 times 1 vector, and plus epsilon high. So epsilon low will be built with 0.1 and 0.15, and epsilon high will be 0.2 and 0.25. Good. The thing is that we have two inequalities in here and in here. In fact, they are 4 inequalities because we have 2 inequalities for each output. And in MATLAB's quadratic programming code, we need to put all the inequalities together. So we'll first move my unknowns to the left side in each of the inequalities, and later on we will stack them as follows. This first inequality may be expressed like this, and well, just to have my unknowns at the left hand side, because decision variables will be control actions. I wish to find the feasible U. Well, the thing is that this is the way in which MATLAB's quadratic programming code needs this equality. Also, regarding this second inequality, we just move HD to the right hand side of the inequality, so we'll write it like this. Later on, when looking at actual code, we will stack these two inequalities in a suitable way. For the moment being, that we have the constraints on my manipulated variables U, apart from, of course, the upper and lower bounds given by the increments. And if there is a feasible U, then our problem will have a solution. Then we'll use quadprog to check that feasibility, but okay, as quadprog is an optimization code, we need to optimize something. What can we optimize? Well, quadprog optimizes any linear and plus quadratic thing, so we may set up this to 0 and this to any invertible matrix, because the only thing we wish to discuss is feasibility. However, if my disturbances were measurable, or I had a state observer estimating them, then a step closer to real implementation would be optimizing something like the options we are going to discuss now. When minimizing this, we may wish to minimize the norm of U, of course scaled, so that all squares mean the same thing. So in that way, we would prioritize the minimum control effort so that error is within bounds. An alternative option may be minimizing the residual error suitably scaled, so that if we have a feasible control action so that the error is 0, then my optimizer would output it, and if 0 error is not feasible, then we will try to find a feasible U with minimum error. That may also be a sensible approach in an application, depending on whether I wish to keep controlled variables at the operating point, or I wish to keep manipulated variables at the operating point and only move them if needed. Any of the two options are sensible, and in fact, we might wish to optimize a combination of them. For instance, if I scale things so that 1 means the same in inputs and outputs, whatever that means for my particular application, well, in that case, minimizing the sum of y scaled squared plus u scaled squared rho equal 1 would also be quite sensible. And in fact, we will do that in the next video, in which we will discuss the SVD approach to this partial disturbance rejection. So for the moment being, if we want feasibility, then this is kind of a collateral discussion. You can skip it, and we can minimize whatever combination of input and output norms we wish. Of course, if we minimize input norm, we will have this H and F in quadprog, and if we minimize output norm, this would be H and F. You can download the materials or just pause the video and examine the highlighted manipulations, but as I said, this is collateral. We just wish at this preliminary stage to ask whether achieving my given error bounds is feasible or not. So we can minimize whatever we wish, and the way to do it is setting these E low and E high vectors, as we discussed earlier on. And if we recall this inequality, I write it like this, and the second inequality, I write it like this. So I will stack minus gain and plus gain into this A inec matrix, and I will stack this thing for each of the vertex disturbances, I1, 2, 3, 4, as this B inec thing, so that this A inec and B inec will be the matrices needed to encode all the needed inequalities in quadprog. Here we have A inec here and B inec there, and well, the remaining bits are setting the minimum and maximum, lower and upper bound of my manipulated variables, and optimizing whatever I wish to optimize, in this case the scaled input norm. So if I run this code, I obtain minimum found that satisfies the constraints in 1, 2, 3 and 4 vertices, so my problem is feasible, which is no surprise because total cancellation was feasible. So we will now increase the disturbance size to see which is the margin we have, the legroom for extra unexpected disturbances. So I've here a zoom factor increasing the vertices of the extreme disturbances, and if I multiply by 2.08, then total disturbance rejection is unfeasible. We see that the vertices of the reachable polygon with the disturbances exceed the boundary of the polygon reachable with my manipulated inputs, but in my partial disturbance rejection setup, all 4 vertices render feasible. So I have a margin of 2.08, but if I increase to 2.09, then my partial disturbance rejection code finds one infeasible vertex. So going back to this 2.08, my partial disturbance rejection within my error limits renders feasible. So what does it mean geometrically? Well, this was the plot for total disturbance rejection, and this is the code that generates the figure we are going to discuss in a minute. So maybe once we see what's the meaning of the figure, you might wish to go back with this video and post a comment if you are interested on how the figures are generated. Nevertheless, convex hull issues and detailed MATLAB polyhedron drawing are out of the scope of this video, in which we just wish to emphasize the control-related aspects. So again, you can pause and analyze the code or download the materials. Let us discuss how to understand the resulting figure, which is this one. The basic idea is that my error limits conform a rectangle in error space, which is here drawn in violet color. So what I did with the code is sort of considering that rectangle as a thick whiteboard marker, let's say, and placing it at one of the vertices of the green polyhedron and moving it along the edge of the green polyhedron, so I get an expanded red polyhedron, indicating the extra range that disturbances might be able to move my outputs, such that when I try to cancel them, I can find a point in the green set so that the error is in the required limits. So with this zoom factor, I expanded my disturbance reachable set up to this point in which the cyan polygon touches one of the edges of the red polygon, and if I expand it any further, then my problem ceases being feasible. So the idea you must get to understand this is kind of the thick marker along the green surface, which tells me in output space the error margin in which I allow the disturbance effect to lie. So good, we'll finish with this, and in a next video we'll discuss how to deal with partial disturbance rejection in the SVD, pseudo-inverses and weighted least squares. For the moment being, we end here. Thanks for watching.